So let's kind of go back for a minute to this zinc hydroxide. So we have zinc hydroxide as a solid, and it's in equilibrium with zinc 2 plus ions in solution plus 2 OH minus ions in solution. There's going to be a KSP table, or a KSP value reported in the KSP table for this particular equilibrium. So we can calculate how much hydroxide is formed here. We can also look at the KF table. And zinc is one of those cations that will form a complex ion with many, many different ligands. One of the entries in that table is you're going to find zinc 2 plus in aqueous solution plus 4 equivalents of NH3 is going to be in equilibrium with Zn NH3 2 plus. And we are going to have a Kf value for this particular equilibrium. Some of the times when you see these equilibria written, there's like a really large arrow going over to the right and a very small one coming back to the left. This is to indicate that most of these Kf values are very, 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 very large. They range sometimes from 10 to the 8th to 10 to the 30th, which means that this equilibrium is going to lie heavily over to the right. So if we compared the solubility of zinc hydroxide in aqueous solution, which has a very, very low KSP, and we looked at what happens when we put concentrated ammonia in here, just like we did in chapters 15 and 16, where if we have a multi-step process, if we add those two steps together, we get one big giant equilibrium expression that's going to have a K value, or an equilibrium constant, that's equal to the multiplied, or the product of the, in this case, the KSP and the KF, or the product of the Ks of all the steps. So what happens here is that zinc ions are going to be placed in solution. And when those zinc ions are placed in solution, they're going to interact with ammonia. A coordinate covalent bond is going to form between these guys, and a complex ion is going to be formed. What that does is that drops the concentration of zinc 2 plus in this solution, and it's going to shift this equilibrium over here to the right. If we have concentrated NH3 or excess NH3 present, the zinc is going to keep reacting to form this complex ion, and it's going to keep dissolving this zinc hydroxide. To set up the overall reaction for this is zinc 2 plus exists as a product in the first reaction and a reactant in the second reaction. So we can kind of, for all intents and purposes, cancel those out. So this gives us an overall equation of Zn OH2 solid plus 4 equivalents of NH3 in aqueous solution. This is going to be in equilibrium with our complex ion, which is Zn NH3 2 plus 2 OH minuses. The K, or the equilibrium constant for this, is going to be the KSP times the KF. In each instance, if KF is very, very large, then K is going to be much greater than the KSP. And this is going to tell us that the equilibrium is going to shift over to the right-hand side, and that in this particular instance, our zinc hydroxide solid will be more soluble in NH3 than in water. So now we don't have to go back and get completely mad at Le Chatelier for coming up with a principle that doesn't work in certain circumstances. It works perfectly. this is proving that his point works very, very well because we have this particular solid. It's going to dissolve, and it's using applications of Le Chatelier's principle to describe the effect that's happening here. So I want to leave you with this comment. When you are mixing chemicals together in the lab, think of these pictorial representations of what's going on. And more importantly, think of the equilibrium established here and how that's going to be affected when you're adding your various reagents. So don't just simply follow a procedure. Think about what's happening for each of those steps.